Hello, everyone. We are back with another episode of Computer Vision Talks, and today we have with us Kwonjoon Lee. Kwonjoon is a PhD candidate in computer science at University of California, San Diego, advised by Professor Zowin Tu. He collaborates closely with Dr. Celio's group at Google Research, and he's interested in designing algorithms and architectures for unsupervised learning, generative modeling, and meta-learning. He was also a research intern at Amazon Web Services during the summer of 2018. And so he received his MS in computer science from University of California, San Diego itself. And we're glad to host you. We're going to discuss about a great topic, ViTGAN. We're going to discuss his paper, and that combines two of my interests, that is GANs and vision transformers. And I'm sure audience will benefit a lot out of today's talk. Over to you, Kwonjoon. Thank you.
Thank you. It's a great pleasure to introduce our work, very recent work. It's called ViT-GAN, training GANs with vision transformers. It's about making GANs work like with vision transformers. Like we want to share our experience in making it work. So I'm Kwonjoon Lee. Thanks for the introduction. So this was work. This work was done in collaboration with the folks at Google Research. Okay, so to begin with, I'll first talk about the preliminary. So first, I'll talk about transformers in natural language processing. So transformers have been heavily influential in NLP field. So let me first talk about how it works. Self-attention is about embedding. So in NLP, there's a token. Token is like each word. So here, like it's linear combination of all other words. And then what is a linear combination coefficient? So for each layer, we linearly combine. We basically linearly combine from all other tokens. And the linear combination coefficient is distance between word I and word J in some embedding space. Okay, and then we repeat this process like L times, and L is basically number of layers. Okay. So this is good. And very recently, transformer has been transferred to computer vision field, and it started to become very popular and influential to computer vision field. So here, so the main question is, how can we transform the computer vision problem into sequence learning problem? Okay, so it's actually very simple. So we divide the image into non-overlapping patches, and each image patch becomes each word in a sentence. To dump into the transformer stack. Then at the end, we are going to do some downstream task based on the extracted embedding. After we process our image sequence of image patches using multiple layers of transformer. So this is very simple, but surprisingly, it works amazingly well. Okay. So let's compare CNNs versus VITs. So they encode different inductive biases. So for CNNs, so the inductive biases it encodes is first local connectivity, right? So if you see the figure on the right, each pixel in the feature map is a result of linearly combining the pixels from the input over a small window, so which is a local window. And also there's a downsampling operation. So downsampling, usually we implement it using 2x2 average pooling. Whereas vision transformers, it has some inductive bias, but like much weaker form. So it is adjacent pixels are grouped together into a patch, as you can see. So we can think of it as a sort of inductive bias. So in the patch in the tokenization stage, right? So other than that, there's really not much inductive bias. I mean, at least not much image-specific inductive bias. Okay, so the question we want to ask is, can we replicate the success of ViTs for image synthesis problem? So there's one question, yeah.
Yeah, I was about to read out. So when we are talking about text embeddings, do we focus on any specific dimension?
I think I didn't quite get the question.
Okay.
I think, can you clarify?
Yeah, Rishi, would you like to unmute yourself and ask the question more clearly, or maybe you can ask, retype it? So are you talking about the, yeah, please.
Yeah, sorry to interrupt. When you mentioned about the NLP part, you mentioned about the tokenization, right? So,
Yes.
for example, in text-to-image synthesis, which is like using SpecGAN, V1, generally they look at embedding of a high-dimensional data. So, do you also look for a specific dimension of text embedding, which you mentioned as like repeat L10s, or is there any other also?
It's really agnostic.
Kwonjoon, I think your internet is also lagging a little bit.
I think, does it sound better?
Yes, much better now.
Can you hear me well?
Yeah, much better now.
I think internet connection is very poor now. So
No worries.
I'll turn up the video for a while then.
Yeah, that's perfect.
This way, yeah, this way it should work better.
Are you clear with the question?
Yeah, I think I would say it's really agnostic to the dimensionality of the input. Dimensionality of input is, we can think of it as some sort of hyperparameter, and we have to just go through a lot of trial and errors, I would say. Does it answer your question?
Yeah, I'll ask if I have some.
Right, right. Another question is that it is regarding the weak inductive bias. What is the reason for the weak inductive bias? Is it because, is it for the non-overlapping patches?
I think by weak inductive bias, I think CNNs have a very strong assumption. For example, local connectivity in the feature extraction stage, and also use of downsampling. And ViTs doesn't have such thing. And the only inductive bias related to image is grouping adjacent pixels together. So by weaker inductive bias, we mean this aspect. And if your question is about why do we prefer weaker inductive bias? Because weaker inductive bias, so if you impose more inductive bias, but more stronger inductive bias, it's more likely that it's going to be wrong.
Right. Okay. I hope that answers Sauvik's question. Please proceed.
So first, we wanted to explore VIT for GANs discriminator. Okay, so as I told you earlier, in VIT's token is a small image patch. Right? So it's easy to repurpose the VIT for GAN discriminator. So I think I didn't talk about how we use VIT for classification. So it's actually easy. So first, there's a linear projection of flattened non-overlapping patches. So you can see 1, 2, 3, all the way up to n. So suppose there are n image patches and there are n tokens. And one small detail I didn't mention before is we need to prepend a special token called classification token, here denoted as star. And we're going to process n plus 1 tokens using transformer stack. And at the end, what we are going to do is we are going to pull the embedding from this classification token and feed it to the MLPs or linear classifier, and we are going to do classification. So that's how we use VITs for image classification. And it's really then easy to change this for GAN discriminator, because GAN discriminator's job is to classify whether the input image is real or fake, right? So we're going to just change the final MLP into binary classifier, real versus fake. Okay, so this part is straightforward. Okay, so first thing we tried is to keep the problem simple. We maintained CNN generator from StarGAN2, and we just changed the discriminator to VITs. Okay, so then here's a problem happened. So the curve here shows like the plot of gradient magnitude over the course of the training. So we can see this is clearly problematic. So there's a lot of gradient spikes, which really should not happen. So there was a very high variance in gradient magnitude. And of course, we tried very hard to solve this problem. We applied all known regularization tricks, such as R1 penalty, spectral normalization, data augmentation, consistency regularization, stochastic depth, gradient clipping, and so on. But so actually this is a best curve we could get by applying all well-known tricks. Okay, so why this gradient sparking is harmful? So the problem here, another problem was we were tracking the training accuracy. By training accuracy, since GAN discriminator is a classifier of classifying real versus fake, we track the accuracy of this classification. Okay, so this blue curve is behaving very this is pathologic because whenever there's a big spike, you can see this classification accuracy actually drops a lot. And whenever it drops, we can see, so the third curve is inception score, higher the better. So this is a standard metric for inequality. So we can see inception score actually drops whenever classification accuracy drops. And the green curve is like our very final version, which was by applying our novel techniques. So we can see green curves actually behave like much better. Okay, so we're going to talk about what is the key to transforming this blue curve into green curve. Okay, so one thing we discovered is that standard dot product self-attention is not Lipschitz. So in other words, gradient of output with respect to input can be unbounded. So and enforcing this Lipschitzness was turned out to be extremely important for stabilizing GAN training dynamics. Okay. So to repeat the magnitude of this attention output with respect to the input of this self-attention layer can be unbounded. And of course, we tried regulating the matrices. So we apply spectral norm. Also, we tried applying gradient penalty to this layer. All of these things really did not help. So takeaway from our experiment was regularizing projection weight matrices.
Kwonjoon, for someone who is new to spectral norm, can you just briefly describe it? What is it?
Yeah, I'll talk about it in the next slide. Actually, I have it in the next slide.
Great.
So, okay. So then how can we make this L2 attention, make this attention layer that just, so it was easy. Change the distance function from dot product to L2 distance. Okay. So let me actually briefly describe how self-attention matrix works. So given an input token, so let's say there are L tokens, then we just embed these input into query vector, key vector, and value vector. So we just embed it into some space using linear projection. And since we have query and key, we can compute the inner product between query vectors and key vectors. So that results in L by L matrix, which is a measure of similarity between each token to all other tokens, and there are L tokens. So that's why the dimensionality of this matrix is L by L. And based on this similarity, we're going to linearly combine the value vector. So here, the final result is this dot product. Like minor detail is that we pass it through the softmax layer, but that's actually not very important for the concept. So we just multiply this attention matrix and the value matrix. Okay. And the way to fix Lipschitz problem of attention is very simple. Just so main component is to change the distance matrix. Distance metric when we compute the distance between tokens. Okay, and so the first component was we need to use L2 distance metric. So change from dot product to negative L2 distance. Another component is we need to apply weight tying. By weight tying, we need to make the query matrix and query projection matrix and key projection matrix the same. So that was the part. So we tried applying L2 attention, but unfortunately it resulted in significantly worse inception score. So first, when we apply spectral norm to the VIT discriminator, FID was around 10. If we added L2 attention on top of it, FID become over 100, which is very, very bad. Okay, so we were puzzled why this is happening. So let's actually revisit how spectral norm works. So spectral norm works by dividing each weight matrix in the network by the singular value of the matrix. And the spectral norm of each matrix W is, in other words, is largest singular value of the matrix W. Okay, it's very simple. So it's about normalizing weight matrix using some constant, and the constant itself is largest singular value. Okay. That's spectral normalization. And we discovered a simple fix to this spectral normalization process can fix the problem of very bad FID. So we were inspired by another paper in ICML there's a theory paper that says large spectral norm helps preventing token uniformity. By token uniformity means at the end of self-attention stacks, transformer stacks, all tokens become similar to each other, which means a useless embedding of the sentence. We want to avoid that. So basically, we want to keep this spectral normalization because it is really helpful for making our transformer stack Lipschitz. But on the other hand, limiting the spectral norm is harmful for transformers. So our heuristic was multiplying it by a large constant after this spectral normalization step. So by large constant, it is some constant larger than 1. And there can be many different choices, but our choice was simple. We just multiplied by the spectral norm at the initialization step of the weight matrix. That was it. And after that, this drop, FID improved a lot. Okay, so takeaway from this part is that self-attention can be very sensitive to the Lipschitz constant, and it requires special care when we actually do spectral normalization. Do you have any questions until this part?
None in the chat, and I am also pretty clear with the concept so far.
Okay, so now move on. Okay, to summarize, I think we started with this blue curve, which is baseline. And after
just one thing,
techniques,
just one question. When we were talking about having a gradient variance, can gradient variance also indicate abnormal data?
Abnormal data? Did you?
Yeah.
That's an interesting question.
Mm-hmm.
I haven't quite thought about that aspect, but yeah, I think it's possible if data itself is very difficult, but normally, like in typical training setting, we just deal with very clean and IID data. So that would not arise very often. Right. But I think this can really happen for training settings like GANs or reinforcement learning, because the training data itself is keep changing and it's like non-stationary, right? Because in GANs, one part of training data is real images, but other part of training data is fake images, which is keep changing. So because of this non-stationarity in data distribution, I think it might be causing like unstable gradient problems.
Right,
I think that's interesting.
Thank you. We can proceed.
Yeah, okay, I'll proceed. So there was a discriminator part, and let's talk about the ViT generator part. To recap, in ViT, each token is a small image patch. And in designing, so left-hand side shows ViT-based discriminator. So in designing ViT-based generator, so our main approach is make ViT-D upside down. By upside down, so let's actually talk each step one by one. So the first stage of ViT-D is converting non-overlapping small image patches into the embedding. And then in light of that fact, the last part of transformer generator should be based on some embedding. We want to convert that embedding into pixel space. Okay, so that's the very last part of ViT-G. And of course, we go through transformer encoder. And also transformer encoder is in both ViT-D and ViT-G. Okay, that's pretty straightforward. And of course, there should be the positional embedding, 1, 2, 3, all the way up to n, injected to the transformer encoder, because transformer cannot work without the positional embedding. So this positioning encoding 1, 2, 3, all the way up to n represents n patches, n non-overlapping patches. So this is transformer part. And another thing I should have mentioned is, so given this pixel rendering of n non-overlapping patches, what we are going to do is we are just going to stitch n patches to form a whole image. Okay.
Another question: when we are talking about how to inject the latent noise, is this the same as the latent space, right?
Yeah, it's same as latent space. In GAN, I think we just typically inject Gaussian noise to the input of the generator.
So in an autoencoder, we often have this difference between a sparse or a dense latent space. Is such kind of a thing similar in this situation also, or not?
Might be the case, but in GAN, I think one nice thing of GAN is that even if we don't inject a very fancy structure into latent, we are just going to throw in some random Gaussian variable into the generator, and throughout this GAN training procedure, it'll magically figure out how to convert very simple latent distribution into the distribution of fake images, which closely mimics the real images.
Okay, thank you. I understand.
I think there's another question.
Yes, there is, but I'm not very clear about this question. I guess it is asking how learning positional embedding for noisy synthetic data in a sensible way. I'm not clear about it. Sorry, can you reframe it and post it again? I'm not very clear about your question. Can you understand it, Kwonjoon?
Can I ask like in?
Yeah, please
Okay.
do.
So the positional embedding are meant to learn the location of the pixels, right? Because in general transformers are positionally invariant. So now when you are injecting noisy data, which has anyway no sense of any position, means any sense of pixel to pixel relative position is not there. So why it makes sense to learn any positional embedding for anyway the noisy data?
Okay.
Can you just not completely remove the positional embedding, because what you are trying to learn through positional embedding noise?
Kwonjoon, is it clear, or do you want me to repeat it?
No, so the reason we use positional embedding is that this transformer layer, self-attention layer, is really invariant to permutation, right? There is really nothing encoded about positions at all, right? We just, this layer is really agnostic. It has no knowledge about position. We're just going to compute the pairwise similarity of the embeddings of each token, right, between all other tokens, right? So if we don't inject positional embedding, there's no way we can judge. So here, by injecting positional embedding, we want to judge the importance of each token based on not only the content, but also based on the location of each token. Okay. So, okay, let's go back. And I think the main question here is how to inject latent noise Z, because this part is not present in ViT-D, so it's not that straightforward. So we experiment with different options. Let me introduce we try 3 different options. There's one question: how to recognize a neighboring pixel of a particular image? So we just like brute forcely. This is a hyperparameter. So let's say we're going to group 4 by 4 neighboring pixels into a patch, and we're just going to dump it to transform encoder. Does it answer your question?
Yes, it does. It does. It is clear.
Okay. Okay. So I'll move on. So how to inject latent Z? Let's assume we are going to. So Z here, in our case, was Gaussian noise, white Gaussian noise, and we just pass Gaussian noise into few layers of NLP, and let's assume that we have a intermediate latent space, and we just call that variable as W. And this is a trick developed in seminal work named ViTGAN 2, and let's suppose this is a good thing to do. Okay, so first option was to copy paste the same latent variable W over all positions. So this is kind of dummy. So we copy paste W over all patches in an image, and we just feed it to the transformer encoder and get all patches from an image. This looks really dummy, but actually it works pretty well. We'll talk about the result later. Okay, so second option was to create a token for the latent variable. So this is similar to classification token in the VIT for the discriminator. So we create a special token, and in this special token we just add this like intermediate latent W. Yes, so the question is, how is the mapping network that outputs W vector trained? Yes, it's part of end-to-end training. Yes. Okay, so the very last option is to modulate the normalization layer with the W vector. So this kind of trick was used in a famous work of ViTGAN and also self-modulated batch normalization. Let's revisit how layer normalization works. So layer normalization, so given feature map HL, so first we're going to normalize by subtracting mean and divide it by variance. And then we're going to multiply it by gamma and beta, which is a constant matrix. And these two matrices are like learned end to end by backpropagation. This is vanilla layer normalization. And self-modulated layer normalization is only different in how we so in this constant part. So this is kind of interesting thing because so given our latent variable W, we are going to output gamma and beta, which is a linear projection of W. And we are just going to feed those linear projection, gamma, beta, into layer normalization. So this is an interesting way of injecting the latent noise into the transformer stack. So this is, in a way, a stronger form of conditioning the output based on the latent W, because we add this information to all intermediate layers which use layer normalization. Okay, so we introduced 3 different options. Okay, so that was it. So when we developed these 3 variants, we first developed based on CNN discriminator, and we just change the generator into ViT. And it worked pretty well, and we got very excited. Okay, then we tried to combine ViT-G and ViT-D together. So here's what happened. So if we train ViT-G and ViT-D together, data augmentation leaks into generator sample from the very beginning of the training. So here we use a heavily influential technique called differentiable augmentation, which was introduced in last NeurIPS. So here, what was discovered in this paper was that if we apply data augmentation to both D and G, we should not see the data augmentation artifact, right? Because applying data augmentations such as like brightness, contrast can be problematic because the artifact from such augmentation might leak into the generator sample, right? But what they showed is that if we apply this augmentation into both training of D and G and make the augmentation operation itself differentiable, the augmentation actually nicely cancels out, and we don't see the augmentation artifact at all. But like very interestingly, when we train with both ViT-D and ViT-G together, we saw this kind of brightness augmentation artifact leaked into ViT-G, right? So in a way, it was our ViT network was so powerful such that it was even memorizing the data augmentation itself. Okay, so we want to solve this problem. So our diagnosis was first, in order to do this, we monitored the binary classification accuracy of the ViT discriminator. So this gray curve is ViT-D plus ViT-G. And the problem was very obvious. So D becomes very confident from the early on. It goes all the way, almost start from 80%. It actually goes all the way up to 90%. So if D becomes very confident, it implies something's going wrong. So in GAN, ideally we want the generator sample to be very hard to be distinguished by the discriminator. So we hope that this discrimination accuracy stays close to 50%, but it was not the case when we trained ViT-G together with ViT-D, right? So this orange curve is like from StarGAN 2, we can see the training dynamics is like pretty healthy. It stays between 50%. It goes all the way up to 65. You can see this is pretty good dynamics. Okay, then how can we solve this problem? So here are the things we tried. We tried many things, but this is one thing which was pretty useful. So this looks very dummy. So first thing we tried is decrease the learning rate of D. Okay, there's a question. Did you try out?
Actually, there are two.
Let me see. What is the role of Fourier embedding that we passed to? For Fourier embedding, we're going to talk about it later. Okay, for the adaptive discriminator augmentation by NVIDIA, we actually incorporated like some components from their paper, but like it was not fundamentally solving the problem. So like we borrowed like, for example, like very strong augmentations from ADA paper. So it mitigates the problem a little bit, but it really didn't fundamentally solve the problem. Okay, so first thing we tried is decrease the learning rate, because the problem was discriminator being too powerful or overconfident. So make the learning of D slower. Then it becomes this greater. So you can see the problem actually gets slightly better. And on top of that, we also try adding stronger augmentations. And also, if we do that, the training curve like looks much better. It becomes this sky blue colored curve. So this is a result. So by adding these two techniques, we were able to get inception score of around 8.8. But as a reference, vanilla StarGAN 2 can reach about inception score of 9.3. So we are still far away from StarGAN 2. Okay, so here is another solution which works well, and we tried. It was not introduced in the paper, like in our archive paper, but this is what worked pretty well. So one solution is use components instead of linear projection of non-overlapping patches for token extraction. So this is also known as hybrid ViT in the original ViT paper, because we sort of combine CNN and transformer, as you can see here. So for example, let's suppose our input image is 32 by 32, and we pass it through two ResNet blocks. Then we get the feature map of 8 by 8. Then we can interpret this into a sequence problem of sequence length 64, right? Because we can just flatten 8 times 8 into 64 sequence. Okay. And actually this worked pretty well. Vanilla ViT, our inception score was around 8.8. Hybrid VIT inception score was around 9.4. So this was a good solution, but we wanted to go further because we wanted to explore whether image generation can be achieved without any convolutions or pooling. We wanted to go further, so we tried a different route. So here's the motivation for the second solution. So we thought about why does ViT-G plus ViT-D behave so much worse than ViT-G plus CNN-D? It's because ViTs are much more expressive because of weaker inductive biases. So using weaker inductive bias give more degree of freedom, but at the same time there's more risk of being overfitted. Okay, so to see what kind of biases they capture, so that's, for me, I think one good way of understanding the inductive biases of two different networks is just to see random samples from untrained generators of two different networks, right? So this really represents the natural state of two networks. So for CNNs, if we just feed Gaussian samples, we can see the output is kind of smooth and continuous. And this is mainly because the repeated application of convolutions and also bilinear upsampling operations. So basically, CNN-based generators start from the feature map of size 4x4 and repeatedly apply upsampling until we reach 32x32. Because of that, we can see like sort of smooth images. In contrast, if we plot out the sample from Yeti, it's really hard to find any patterns like natural images. It's really non-smooth. So we thought this is a problem. Okay, so we wanted to fix this without using convolutions or upsamplings. And we were inspired by the recent progress in 3D synthesis field. So there's a very influential work last year called NERF and NERF. So let me talk about what that is. So let's first talk about coordinate-based MLP. So it's kind of a strange network. So it learns a mapping between coordinate V and pixel value Y. So it's also known as implicit neural representation. So to give an example, so this coordinate-based MLP takes the coordinate. So for the 2D image case, it takes X and Y and pass it through some layers of MLP, and at the end, it'll output RGB. So in order to generate the entire image, so we need to feed 1,1 and get the pixel here, 1,2, get the pixel here, all the way up to, let's say, n, and get the final pixel. So this is how coordinate-based MLP works. But if we just naively do it, it doesn't work well. And what so-called NERF or Fourier feature network. So what these guys have discovered is that MLP, so if we MLP followed by a Fourier basis projection can fit high dimensional signal well. High dimensional signals such as like image, 3D, video, sound. So Fourier feature allows a convenient way to learn continuous signal without much assumptions about the problem domain. Because Fourier basis, by Fourier basis, they just concatenate sine and cosine functions of different wavelengths. So we do Fourier projection using this basis and dump it to few layers of MLP here. And as a result of Fourier feature, we can see the stark difference between the image on the top, which has no Fourier feature, and the image on the bottom. So we can see this is very useful for representing all kind of continuous signals without adding much assumptions about the domain. So we thought this can be very useful for our problem. Okay, so this is a motivation for the second solution. The second solution is to use Fourier feature network for pixel mapping in the generator. Okay, so to generate each patch, we are going to take feature from the transformer encoder corresponding to, let's say, ith patch, and another input to the Fourier feature network is the coordinates, to be precise, coordinate embedding of each pixels within a patch. So let's suppose one patch is of size 4 by 4. Then we have to feed the pixel coordinates from 1, 1 all the way up to 4 by 4 to generate 4 times 4 pixels, right? So this is how it works. This is very simple. Okay, so the summary is that because of this Fourier feature network, we were able to match the result of StarGAN 2, which is based on CNNs, without using convolutions or pooling. So the paper, like this is a table in the paper. So we try on the combination of different backbone structure, different latent code injection method, and output mapping method. So the conclusion is that it's always better to use Fourier feature network instead of the naive linear mapping. And this option C works the best, and followed by option A. Option B performs, I think, slightly worse than option C. And option B, interestingly, is much worse than other options. So I had thought option B is the most natural way of doing conditioning based on latent for VITs, but unfortunately it didn't work. Did you try to combine Fourier features and convolutions? I didn't try combining Fourier feature to convolution. Why such aversion to convolutions? That's a good question. Actually, convolution works pretty well. But one thing to note about convolution is that we find that it's really hard to tune these convolution networks. I don't know why. We just find this simple 2-layer Fourier feature network actually works very well without much tuning. Like it works well across different resolutions and things like that. We don't need to tune. Actually, we didn't tune at all when we like scale up the resolution. But it's possible that I didn't engineer it well. So that's one point. Another point is that so main motivation of this work was to actually initially this project was about video generation, and we wanted to design a network which is almost modality agnostic. So the reason we showed our method of image generation is because it's just a simple test bed of our idea. But we hope that by adding as least inductive bias as possible, it should be very easy to extend our technique to other modalities in the future. So that was the main motivation. Are you aiming for foundation models? I mean, I don't want to call it that ambitious, but I mean, that's what I hoped for. Yes.
Okay. Please feel free to put more questions. I guess we are nearing to the end of the presentation, and we'll take all of them up in the end.
Okay, so I think I'll wrap up pretty soon. So this is coming to end. Okay, so key results on standard benchmarks. So we tried CFAR10 on 32 by 32 resolution. Celebi, Elson bedroom, we tried on 64 by 64 resolutions. And yeah, so this is the result. So first category of methods are based on CNNs, ViTGAN, StarGAN2. Second category is baseline transformer-based GAN methods. TransGAN XL is prior work on transformer-based GAN methods. Okay, so the third category is our method. So we can see that compared to the baseline transform method, ours works just much better. And we can see transformer-based GAN has started to rival the image generation quality of CNN-based GANs. This is the main takeaway from this table. Okay, let's see random samples on Elson bedroom data set. So the first is from StarGAN2. Second is vanilla VIT. So like prior baseline transformer GAN methods really doesn't scale up to high resolution or complicated data sets. So third is our VIT GAN. We can see ours performs like better than others, especially on this data set. And like I observed many samples, and it seems that VITs like performs like more complicated scenes. Like I had an impression that StarGAN prefers a like more simple in terms of texture. I think it prefers a very smooth and like white beds you can see, whereas VITs prefer like more diverse textures you can see. Okay, and here let's talk about mixing VITs and CNNs. So, okay, so the first row is ViTGANs results. Second row is StarGAN's result. So third row is about combining like vanilla VIT and StarGAN2. It doesn't work that well due to unstable training problem. The ViTGAN, if you change it to ViTGAN, it actually works slightly better. And finally, actually, this is a interesting fact. This is a combination which works the best until now. So we find that combining StarGAN2's discriminator with ViTGAN's generator work the best. So we're actually still investigating why this is the case. But based on this intermediate result, what we conclude is that for discriminator, it's still better to use StarGAN2 compared to ViTGAN. But for generator, it's much, I think, useful to use ViTGAN compared to StarGAN2. So that's what we get from comparing this entry and this entry. And also compare, yeah. Okay, so like why StarGAN2's D much better than ViTGAN? So this is just sort of intermediate study. So this is not what we included in the paper, but we discovered that StarGAN2 use additional feature called mini batch standard deviation. So what they did is they compute the standard deviation for each feature in each spatial location over the mini batch. So this way, this feature actually has a good notion of diversity of samples within a sample, within a batch. This is because that's what standard deviation is meant for. So by using this as additional feature, actually, this seems to be very beneficial. So the first row is like baseline. We actually ablated, we disabled the mini batch standard deviation from StarGAN2, and the result actually drops quite significantly. And another thing I forgot to mention is that ViTGAN does not have this standard deviation technique. And we expect that by incorporating this technique into ViTGAN discriminator, I think the result, there's a room for result to be much better than this number of 9.3. Okay, finally, the effect of data augmentation. The first category of method is based on CNNs. We can see data augmentation moderately help for both ViTGAN and StarGAN2. The second category is ViTGAN. You can see if we disable the data augmentation, the result, the performance drops significantly. It's almost impossible to train GAN, transformer-based GAN without data augmentation. But this is kind of expected because the original VIT paper says that having large data set is really, really crucial for training VITs. So this is kind of expected because VITs impose much weaker inductive bias, and which means we need much more data set to learn useful priors about the images. Okay, so finally, let's talk about how we scaled to higher resolution images. I think for higher resolution images, actually, we were able to scale it up to 120 by 128. 256 by 256, we didn't quite finish the experiment due to limited time. But we were able to do very well on 128 by 128. So here's how we did it. So we actually had to use convolution plus downsampling for this high resolution. So the method is very simple. So before the transformer stack, so in D, we just apply this convolution 3 of stride 2 plus leaky ReLU 2 times. And finally, we just apply 1 by 1 convolution stride 1. And that results in 8 by 8 feature map, and we just convert it into the sequence problem of sequence length 64. So this is the only modification you need to scale it up to high resolution. So this is the result on 128 by 128 Elson bedroom. So on this data set, ViTGAN is better than StarGAN2. Another result we had is combining StarGAN2's D with ViTGAN G. Again, this is much better than vanilla ViTGAN. So it really seems that currently the best option is to mix CNN-D and ViT-G. Okay, I think this is all slides I have, and thank you very much for your attentions. And yeah, I'll take any questions you might have.
Yeah, it was a great yeah, please go ahead. Please go ahead, Nikhil.
So what is your take on mode collapse problem using transformer-based GANs? So there,
I think mode collapse, as I mentioned here, I think mode collapse is due to exceedingly powerful capability of VITs, and I think one way we solve mode collapse is just gradually adding more inductive bias to VITs. So in other words, we want to make it less powerful by adding more assumptions, such as, for example, one assumption we can add is convolution, right? Like local connectivity in the lower layers of VIT. So you can think of this resonance stack as lower layer of VIT. So that's one way to do. Another way is introducing the assumption about smoothness by using this Fourier feature.
Okay, great. I hope that answers your question, Nikhil. And if anyone has any questions, you can put it down in the comment section, or you can unmute yourself and go ahead. Till then, I want to ask you, how much time did it take you to finish the whole project, Kwonjoon?
I think this development of this entire method, I think, took about 2 months. But other than that, actually, 2 months is really short. But it was possible because I was working on like very related problems. So I had all the compute and like GAN training code base set up so that I can just dive into problem and analyze the essence of the problem.
Right.
So like main challenge in this project was about the compute time and compute infrastructure, and also getting the right GAN training code base was really challenging.
I see. So the compute time and the expenses were heavy, so it would be tough to reproduce the results, right?
It's not very tough because, for example, nowadays there are many ways you can easily obtain like compute resource. For example, this research was actually possible because Google Cloud provided me TPUs. Actually, anyone in the world can apply for the free TPUs, I think.
Okay.
So,
Yeah, right.
so I'm not officially with Google Research, but Google just generously provided me with free TPUs so that I don't need to pay for it.
That's great. That's great. Okay. There's one question in the comments. Did we cover this one? Any thoughts to incorporate multiple modalities?
I think that's a great question. I think this is also the problem I'm very interested in. I think it seems that transformer is very capable in incorporating multiple modalities because as long as we can convert all different modalities into sequence learning problem, we can just dump the very long sequence into transformer and that transformer process it. That's I'm just talking about the very high level explanation. But multimodal learning should be definitely much easier due to the help of transformer.
Right. So I think these were the questions, and we are done with all of them. Thank you so much, Kwonjoon, for agreeing to present the paper and giving this talk. And you took all the questions from audience, and it was really, really very helpful. Thank you so much.
Thank you.
Thank you, Kwonjoon.
Thank you so much for inviting me.
Thank you.
It was a pleasure.
Right. We look forward to more great work from you.
Thank you.